Very nice to be here. Thank you very much for the giving me the talk. Okay, so my interest is in studying protoplanetary disks and particularly why we get the diversity of extrasolar planet systems that we do. So I will be talking about our radio observations of protoplanetary disks on behalf of the PEBBLeS team. So PEBBLeS is a survey that looks for pebbles, small rocks in young protoplanetary disks. So if we're interested in imaging the planets that are around stars rather than the free floating planets, we find that the ones as shown in this work here that are at tens of AU from their star and several Jupiter masses are quite rare. So the probability function suggests most likely only about 2% of stars have such planets. And that's in this large survey just completed and published from the GPI instrument. Okay, and maybe there are a few more around the most massive stars, but something in the ballpark, 1-2% maybe. Okay, so this is not actually a trivial number. They're rare, but if you think about hot Jupiter planets, the first discovered, these are only about 1%, in fact, of the true population around stars. So this is a significant population of these extremely massive planets very far from their star. So as a disk person, it seems fairly natural to me that these should at least occasionally form. So if you have a massive disk around a young star, then parts of this disk can be gravitationally unstable. So a local overdensity can collapse just under its own gravity and create a planet in orbit. Excuse me. Okay, so the physics of that seems fairly straightforward, but the observations are not. So we have beautiful observations of details of circumstellar disks, including the gases, the dust component. What we don't have is a good handle on the chemistry. So converting those measures directly into the mass of the disk is really difficult. And really uncertain. And so we don't know how many disks are relatively massive enough to their host star, 10% or more perhaps, for this gravitational instability effect to actually occur. So I was really interested to see this year this very nice observation made. So what we see in the plot is the rotation of gas in the disk, not the intensity. So if it's all smoothly rotating, it'll all be blue shifted on one side of the star and red shift on the other. And what they see in their ALMA data is that there is a point where there is a perturbation of that smooth pattern of velocities, and they interpret that as a gravitational instability existing in this disk. Okay, so first starting to see this process in action. But of interest to us is what happens to any of these distant massive planets that form. Do they simply create the imaged population, or does something else happen? So this meeting just really got me interested in this idea of whether massive planets far from their star might be the most vulnerable to ejection. Okay, so we'll see later about the microlensing detections of free-floating planets. It looks, if we plot that population, and I believe Sumi-san will be speaking later, that there are not very many microlensing detections above the Jupiter mass regime. Okay, so on this sort of part of the plot. And this is what simulations of planet interactions in disks suggest as well. So in the theory, which is the orange histograms, it depends a bit how the simulations are done, but certainly the more massive planets appear to be less frequently ejected. I guess that's what you'd expect. If the planets are interacting, the lower mass ones will be more vulnerable to being thrown out of the system. But what is of interest is situations, and we've just heard about the importance of environment, that if star systems are interacting with each other, then the worlds that are far from their star are presumably then the more vulnerable to being ejected and thrown into space. So this is where the radio imaging of the disk comes in, and in particular the hunt for objects that might be protoplanets. So we're looking at disks at ages of 1 million years or a few million years when the planets are actually forming. Apologies if this is a bit basic, but disks may not be what most people are familiar with. So you've probably seen images from ALMA of disks, which look very beautiful and have a lot of structure. And ALMA observes at millimeter wavelengths or a little shorter. So why would we go to centimeter wavelengths? So the reason that we're doing that is because dust particles are very inefficient emitters of radiation at wavelengths much larger than their own size. So if you see centimeter wavelength radiation with a spectrum consistent with dust, you're actually seeing centimeter-sized bodies like a marble or a pebble or something. And for planet formation generally, that's a key stage to sticking rocks together to get larger and larger bodies like asteroids, cores of planets, and so on. That's why we're doing this. The secondary reason is that this is a black body emission spectrum. So as you go to long wavelengths, it gets crazy faint. But also, the opacity of the disk is much less at the longer wavelengths. So you can see through all this obscuring material, all the gas in front of the disk midplane, much better at centimeter wavelengths. And that's important because the midplane is where we expect the planetary cores to form. So ALMA may be giving you the most beautiful pictures, but not necessarily the best representation of where most of the bulk of the mass is. Okay. So the very first observation of radio observations of a protoplanetary disk was only made 20 years ago. So we started observing with a very large array shortly after that, and we got this nice image of the HL-tau system. So you can see the whole disk is larger, the white ellipse. So we're only seeing in the color in the middle a smaller part of the disk. So maybe that's where the small rocks are forming, or we also are a bit sensitivity limited. The fascinating thing about this was we discovered a secondary feature marked B, which is a candidate protoplanet. So that was a 4.5 sigma detection at the time of an extra clump of material in the disk that could be a massive planet, in this case about 70 AU from the star. So that inspired us to go on and start PEBBLeS, which conveniently does what it says. It's the Planet Earth Building Blocks Legacy e-MERLIN survey. So we're looking for clusters of dust of only a few Earth masses to see if we can see quite low mass planets forming, but also the whole variety of what's forming in protoplanetary disks. Okay, and this was done with e-MERLIN, which is the UK's network of radio telescopes, and it is the premier thing for this kind of work because it has very long baselines, up to 200 kilometers between the different telescopes, so it's got a very good angular resolution, which at the distance to the nearby star formation regions translates to only a few AU, which is perfect for studying the structure of disks. Okay. So all the previous surveys were done at about 9 millimeters wavelength, so we are 5 times longer in wavelength, which for a black body spectrum means we've got 25 times less flux or thereabouts. So this is insanely hard, and it's taken us a long time, and we're about a 1,000-hour survey at this point. But we are trying to get the survey paper out in the next few months and data products available for everybody to look at. Okay. So what do we see? So this is the prototype image that Katie Hestley, who was then the postdoc on the project, has worked really hard on. And we see the disk axis runs this way, and we see a jet feature. The jet is expected to vary over time as more material is emitted by the star, whereas the disk should be a relatively constant thing, and that's what we see. But we were fortunate enough as we were doing the tests with the array to get data in 3 separate years. And in all of those, yes, we see the disk, but we also see it's brighter on the left side. So this asymmetry extending to the left is a real feature. It's moving with the star. It's present in 3 different times. Okay, so we're saying that's a really solid detection of there is a lot of action on one side of the star and potentially material clumping together to form a future massive planet. Now that we've completed the survey as a whole, as I mentioned, this is really hard. So we have 10 fields and 10 primary targets in that. So they're about 100 hours of telescope time each. What I was really surprised to see is how many of these we see a disk that with modest significance looks to be asymmetric. So there's the DG tau one. There are features, there's a detached secondary clump in this one. and here in this one. HL Tau, we're not actually sure where the clump is at the moment. So that was the one we did in 2008 with the VLA. We haven't necessarily recovered that one, but at least 3, we see an extra feature in the disk. And what do these ones have in common compared to the rest of the 10? These are all stars with wide binary stellar companions or something nearby in the field, thought to be a distant companion star, but not much else in common. Okay. So this got me thinking about where do the protoplanets go? So maybe these features, okay, maybe they're not necessarily all real because of the signal to noise, but I'd be really surprised if all of these are just noise misinterpreted. So maybe they're not all permanent. Maybe this could be a temporary cluster of dust, which then somehow disperses back into the disk. Okay. Maybe they do all go on to form distant planets, in which case we have an incidence of 30 to 40%. Modulo the small number statistics. That seems crazy large because we saw that the incidence of distant imaged planets imaged in the optical is like 2%. So those two numbers don't seem to match up. So an explanation could be that some of these protoplanets are actually ejected and become free-floating massive planets. Okay, so this is the point we're kind of at of seeing how well this might agree with theory and other observations. So generally, these stars are not in particularly dense clusters, so I would not have expected the star system interactions with just random passing stars to eject them. But it might be because of the wide companion star, or perhaps an instability within the disk. So in a theoretical simulation, you may form several protoplanetary-like clumps at the same time. The illustration is actually from a discussion meeting at the Royal Astronomical Society in January, so I just took something from their poster. But the simulation suggests you could have multiple things produced in a massive disk, and so maybe they can interact and some of these are ejected. The bit that excites me is whether we can observe this directly to see if something ends up as a free-floating object or is neatly orbiting around the host star. So as I mentioned, the resolution of radio interferometry is high. It can be a few milliarc seconds. And so we can actually see if we can recover an object that it is actually moving. So this is what I'm excited to be doing for HL Tau. It's protoplanet at the moment. The discovery was actually done earlier. We see the blob in roughly the same place about a decade later. And then a decade after that, we're trying to recover it. So these are the positions, this is the orbit it would have that we would be able to see a section of about 20 or 30 degrees of motion. If it is bound to the star, we know it should be, from velocity information, it should be going around that way. So it should have a track like that. So if we can recover it in the latest image or a future image, we should be able to say whether it's bound to the star or in the process of being ejected. So the final thing I was going to say is there's a lot more potential to do this with radio observations of disks. So the next generation of facilities, the next generation Very Large Array and the Square Kilometre Array will have amazing sensitivity and hopefully long enough baselines for the high resolution to build on studies such as this one by John Tobin's team. So for example, they looked at the Orion star formation region, which is packed with disks and is a much denser stellar cluster in the southern sky compared to those available to us in the northern sky. And so I'm really excited that we'll be able to look for candidate protoplanets forming there, and then over a decade or two, be able to see what happens to them and see if they do in fact form any massive planets that are being ejected as we watched. So thank you. That's what I had to say.
Very nice talk.
Thank you.
I was interested whether these asymmetry in disk are only limited to just a wide free-floating or weakly bound planet, or it's possible also to have multiple planets orbiting around that would arise this particular asymmetric shape.
I'm sorry, I missed a little of that. In the HL Tau system or more generally?
No, in general.
Generally, yeah. we're really limited by sensitivity, so there could be multiple objects that we can't really detect, and we're kind of at like, 3 sigma contour in our images. It's also very complicated because we're imaging these complex jet structures at the same time. So particularly we may see, a point source in the image, but if it's in the direction where the jet comes out from the star, we would need a second epoch to say, okay, it's moving with the jet. It's just a clump in the jet, not a protoplanet in the same region. So.
I see. Thank you.
Hi. Really interesting talk. I just had a quick question about the wide orbit companions. When you say wide, what kind of separations are you talking about?
I think we'd be talking about hundreds of AU. I'd need to check the images, but they're not like, they're not like 20 AU or something.
Yeah. Okay, thanks.
So nice talks. So the stellar binaries may also form in a similar process if there is, the mass ratio is high. Is there any significant boundary between the planetary, binary or planetary system?
So all of the stars that we've looked at, their companions are thought to be stellar. So GV Tau south has GV Tau north, and generally they're not necessarily at exactly the same evolutionary stage. One might be a protostar and one might be a pre-main sequence star, but it's fairly well known that these are two objects massive enough to be stars. I don't know of any where we could definitely say that the companions are brown dwarf, for example. Is that answering your question?
Well, if see comparing the distribution, like mass ratio, is there any significant difference between the low mass stellar companion or planetary mass companion?
Okay, yeah. It's difficult at the moment. We haven't completed the modeling that would enable us to turn these fluxes into masses directly. So we can get the masses of dust, but it's much harder to find what is the mass of gas surrounding that, and that's where the chemical uncertainty comes in. So I'm afraid we're really uncertain on what the masses are at the moment, which is why I didn't really talk about it. The clumps that we see in the disks have to be pretty massive, like Jupiter's upwards, for us to detect them, and are probably substellar, but I can't really say much more than that at the moment.
I don't know whether I understood you correctly. You're seeing the radio emission from the disk. Is it possible that you can actually see sort of radio emission from the planet itself due to magnetic fields close to the disk or something like this? Or is this sensitivity not enough?
Yeah, it would depend on the wavelength. So I think if we were observing at longer wavelengths, we could be picking up magnetic activity and aurora on the planet. But I think at our wavelengths of a few centimeters, that would not be strong, though I'm not an expert on this. The interesting one for me with the candidate protoplanet for HL Tau is whether it's faded over the years, and it might be, in that case, an accretion burst onto the planet.
Okay. More questions? Yes.
I apologize if I missed it. In one of your first few slides, you mentioned formation of planets through gravitational stability in the farther region. I might have missed it. What's the range for the mass of that planet?
So in the models, you get a few Jupiter mass object upwards in the gravitational instability. I'm afraid in the actual image I show, I couldn't find in their paper the mass that they detected, but maybe I just didn't read the paper.
But from observational point of view, what would be, is there a way to put a constraint on that?
From the observational point of view, again, we can measure the dust mass and we can estimate the gas mass, which is the majority for these traces like carbon monoxide molecules. Right. But the chemistry is really difficult because the molecules freeze onto the dust grains, and that process is very badly understood. So the step going from the flux to the mass of hydrogen in the disk is really hard. So.
Very good. Thanks so much.